Hi guys, so today we're working on the LONCAPA video solution for problem set 9, and today it's the power winch skier problem. So the problem says the figure above shows a 33.8 kilogram skier being pulled up a hill by motorized gear. The snow that has built up on the skier's skis creates a coefficient of kinetic friction between the skis and the surface of 0.13. The skier is pulled up the 25-degree hill at a constant rate of 2.8 meters per second. How much power must the motorized gear supply? So the picture didn't copy over, but it looks a little bit something like this, where we have our hill, and at the top there's going to be a motorized winch, and then we have our little skier guy right here. Let me do that a little bit bigger. The skier. And we have this tow line connecting him to the winch. So now we can start filling some things in. For starters, we can give our hill an angle, which is going to be theta, and theta is 25 degrees. The other things that we know is we're going to have a normal force, the force of gravity acting on the skier. Sorry, I don't know what's happening with the pen today. We have the force of tension that the tow rope creates, and the force of kinetic friction from the friction with the skis. So the next thing that we can draw in is our velocity vector. So the reason that I'm not doing an acceleration vector is that this says that we are going up the hill at 2.8 meters per second, but it's constant. So because it's constant, what that is going to mean is that our acceleration vector is 0 meters per second squared, because velocity is constant. So the other things that we can fill in from this problem is that our skier weighs 33.8 kilograms. Our coefficient of kinetic friction is 0.13, and I think that's going to be about it for the prep for the problem. So the next thing I'm going to do is I'm going to draw a free body diagram just so we can get a more visual sense for how these forces are all acting without being on an angle. So I'm going to even out our x and y axis. And we have the skier again in the middle. And then we'll have normal force, force of tension, kinetic force, and the force of gravity, which is at an angle because of theta from the hill. And then obviously we have our y and x directions. If we look at this f of g right here, then we can blow that up to a little bit bigger, where now we have, let me save some space. We have f of g, and this is going to create a triangle with our theta being this angle here. And so that theta, as we've already said, is 25 degrees. And that makes this side, FG, cosine of 25, and this one, FG, sine of 25. That'll just make it easier later in the problem when we're trying to figure out the x and y components of force. Alright, so now that we have all this prep done, what we're really looking for in this problem is how much power, we're looking for the power that the motor gear supplies. So our motor gear is up here, it's this power winch, and so the only thing that we can really use to measure that is going to be this tow line. So we can look at our different power equations that we have. There's a lot of them, so let's see. Power equations. The most well-known is going to be power is equal to work divided by time, but there's a few others that I'll write out really quick. So, even though I already said it, I'll just say it again for this power equation, which one we're going to use. We can kind of do process of elimination. We don't really use these down at the bottom very much, so I'm going to get rid of those. The next thing is work over time. We have the potential of finding work because we can find all the forces. However, we don't know the time, so we're going to get rid of this equation. And that leaves us with the next one, which is going to be EMEC over time. But again, we don't have time or any way to find it. So we're going to be doing power is equal to force times velocity. So when we do power is equal to force times velocity, let me write that out right here. So our goal is we're going to find all of the variables to do power is equal to force times velocity. That's our end goal of what we're working towards. All right, and the reason, and this is going to be force of t. So the reason that we did that, so we did F of t because it's the power of the winch, and that acts on the tow line. The only force acting on the tow line is going to be our force of tension. So that's kind of why I wrote that in our equation. Okay, so let's now start solving this for real. So I'm going to make a chart of values just to keep things straight. So E of 0 is the person being pulled up. And so here's our little chart that we're going to have. So E of 0, and we have a lot of different values. We have our velocity value, which we were given. That's going to be 2.8 meters per second. That was given to us right here. The other things that we'll be trying to find are F of t is obviously what we're going for, but the other forces in the problem, I'll just put a spot here in case we need them. Force of gravity, normal force, force of kinetic friction, and let's see, I believe, oh, and then theta. So we also know that theta is 25 degrees, and that's all we know. Okay, so let's start trying to solve this. Let's find net forces first. So we have force net of y, and from our picture, or from our free body diagram, we can determine that the net force of y is going to be F sub n minus the force of gravity, but it's going to be this cosine value, so Fg cosine 25. But the other thing that we know is that acceleration is equal to 0, so this is going to equal 0. F net x is going to equal our force of tension, because that's the one that's going in the positive x direction. So force of tension minus the force of k, which is that one, and then minus Fg, and this time we're going to use the sine component. So sine of 25, and this also equals 0 because the net acceleration is going to be 0. Okay, so we're looking for f of t. That's, again, like I said, our goal. So it looks like we can solve for f of t right here by saying negative f of t is equal to negative f of k minus fg sine of 25. I just moved these around because it's equal to 0. I don't want to work with negatives, so I'm going to multiply it all by a -1. So f of t is equal to f of k plus fg sine 25. And it looks like we are stuck here because we can't do anything without the force of kinetic friction or the force of gravity. So to make our life easy, let's start with the force of gravity. I'll put that down over here. So our force of gravity is going to equal to mass times acceleration, or in this case, mass times gravity, the force of gravity, and that is 33.8 times 9.81, and that gives us a value of 331.578 newtons. I'm going to put that in our chart just so we have it. So 331.578 newtons, and we'll plug this now into the equation. So we have f of k plus 331.578 sine of 25. Okay, so I guess now all we have to do is solve for f of k. That seems to be all that we need. So f of k is equal to normal force times the coefficient of kinetic friction, and it looks like we're stuck again because we need the normal force. I'm going to come down here and calculate that. So normal force is equal to the force of gravity, but it's only going to be this y component because that's the one that works opposite of the normal force. The x component works opposite of tension. So we're going to do f of g cosine of 25, which is going to be 331.578, which we just calculated, cosine 25, and that gives us 300.511 newtons. Again, I'm going to put that in the chart, 300.511. So now we can come back over and we can bring this value into this equation. So we're going to get 300.511 times 0.13. They gave us that value in the problem. And that finally gives us 39.067 newtons for our force of kinetic friction. Once again, just going to put it in the chart. And we can plug this in now. 39.067 plus 331.578 sine of 25. All right, now that we did that, it's just easy. You plug it into your calculator. You get 179.198 newtons as our force of tension. And now we have everything that we need to solve for our goal of power, because we have f of t now, which we solved for here by using all these different equations and the other forces. And our last step is just going to be to find power. So we have power is equal to f of t times v, which is going to equal 179.198 times 2.8 meters per second. And that gives us 501.754, which will round to 501.8. Standard units is watts for this problem. So hopefully that helped. I know it's a lot of steps, but once you really start using and breaking down the forces, it makes a lot of sense. It's just basic free body diagrams and plugging into the equations. And that's all.